This is nuclear physics introductory course. Today we will be talking about radioactivity calculations and examples. I am Dr. Nasir Mirza, and this lecture is about the radioactivity and its numerical calculations. The law that governs the radioactivity is based on the number of nuclei that are decaying per unit time. That is the rate of decay, which is proportional to the total number of nuclei in the sample. And that forms the basis for the law. Let us briefly derive this. If n is the total number of nuclei in the sample, and delta n is the number of nuclei that undergo the decay or a change in time delta t, then rate of change is delta n divided by delta t, which is proportional to n, and therefore we can write a proportionality constant as a lambda. Delta n over delta t equal to lambda times n, and this is our first equation. This lambda is later defined as a radioactive decay constant or a disintegration constant or the probability of decay per unit time. Now we try to find out the rate of change of number of nuclei in the sample. So the dn or delta n is negative because it is causing a decrease in the number in time delta t. So rate of change of n with respect to time in the limit that delta t goes to 0 is given by dn over dt equal to minus lambda times n. So this expression, the number one equation, gets modified into this rate equation or a derivative, the first derivative of n with respect to time equal to minus lambda times n. It is the same as saying that the number of nuclei that are decaying per unit time are proportional to the total number of nuclei in the sample. So as we move further, we can integrate the dn over dt from t0 to t, and lambda being constant can be taken out. And once we integrate, we find that it is natural log of n minus natural log of n naught. N naught is the number of atoms or nuclei at time t is equal to 0, and lambda is the proportionality constant, and t is the time any time, and t0 is the initial time. So the number of radioactive nuclei at any time, any subsequent time, can be found from this equation. We combine these two natural logs, and we find that it is n divided by n naught in the natural log form equal to minus lambda t, or in other words, taking the anti-log on the both sides, we get n as a function of time equal to n naught times e to the power minus lambda t. This equation 4 forms really the radioactive decay law. It states that the number of atoms or nuclei at any time t for the radioactive decay obey this n naught times e to the power minus lambda t, where n naught is the initial number and lambda is the decay constant and t is the time. So if we want to find out the decay rate, this is the rate which tells the number of nuclei that are decaying per unit time. Then we can figure it out using this law. We can form the problem by considering a time interval delta t and get a decay count delta n or minus dn. The decay rate is defined as the rate equal to dn over dt with a minus sign, And we have this n is equal to n naught times e to the power minus lambda t expression for the radioactive law. It is called the exponential decay law. We differentiate it with respect to time on both sides, and we get the rate r. dn over dt is r. So we get r. N naught is a constant. E to the power minus lambda t, when you take a derivative, it brings minus times lambda, and then e to the power minus lambda t. And since this rate r is minus dn over dt, therefore both minus signs cancel each other, and we get this expression as equation 5, which says that r is equal to r naught times e to the power minus lambda t. The decay rate at time t is equal to 0 multiplied by this exponential decay gives you the radioactive decay rate. Once we know the radioactive decay rate, then this equation 5 is basically forming an alternate form of the radioactive law for the decay of the radioactivity, and we can rewrite the equation, first equation, as r is equal to n lambda, and n can be substituted. Now we define two quantities for the radioactive decay. One is the half-life and other is the mean life. Half-life is the time at which both r and n will reduce to half of their initial value. So it is the time, basically it is the time at which they become half. And the mean time is the time in which both r and n will reduce to almost e to the power minus 1 of the initial value. We will define it further, and let's calculate the half-life. The half-life of radionuclide, which is the time to decay the 50% of the initial activity. So T half is the time, and n will reduce to n naught divided by 2. Radioactivity or the reaction rate will reduce to A naught divided by 2. So activity as a function of time is given by A naught times e to the power minus lambda t. We substitute the value of t as t half and A equal to A naught by 2. So A naught will get cancelled on both sides of this equation. We get half equal to e to the power minus lambda times t half. We take natural log on both sides. So natural log of half is equal to this. So natural log of 1 minus natural log of 2 is equal to minus lambda times t half. We know very well that natural log of 1 is 0. And the natural log of 2 is 0.693. So from this equation, we can find out the t half, which is equal to natural log of 2 divided by lambda, or 0.693 divided by lambda. This, the factor which was being used with A was e to the power minus lambda t. This factor has a name. It is called decay factor. Some books write it as a df, which is now, in terms of the half-life, can be written as we can substitute the value of lambda, the probability of decay per second, as natural log divided by t half. So here I have substituted natural log of 2 times t divided by t half. Now we can figure out the average life of the radioactive sample as well. Average life is basically defined as this in a proper form, where t is multiplied with the number at any time t and integrated over all the time from 0 to infinity. And then we divide it with the number from 0 to infinity for all times. So it is the number of atoms which we are using as a weighting factor to find out the average time. So we know very well that n is equal to n naught times e to the power minus lambda t. Therefore, we substitute this into the equation, and then we perform the integration. E to the power minus lambda t integration is easy. Here we have the product t multiplied by e to the power minus lambda t, but we solve this using the product formula and reach at the result that the half-life is equal to 1 over lambda. Remember that half-life comes out to be 1 over lambda. Now we know very well that lambda and half-life has a relationship. The half-life is equal to natural log of 2 divided by lambda. Therefore, we can express the mean life as 1 over lambda and lambda equal to the half-life divided by the natural log of 2, and which comes out to be the 0.693, and 1 over 0.693 is 1.44, which means that half-life is approximately 1.44 times the half-life. Let us solve one problem. The half-life of the uranium-235 is 4.5 into 10 to the power 9 years for alpha decays. Now, question is, what is the activity of 1 gram of uranium? To find the activity, the reaction rates, we would like to first of all convert our half-life value into seconds. Half-life is 4.5 into 10 to the power 9 years. We multiply it with 3.6 into 10 to the power 7 seconds per year, and we get this answer in seconds. Once we have this answer in seconds, then we go further and try to find out the numbers. We know that the naturally occurring uranium is almost all U-238. So a mole of uranium weighs about 238 grams. A mole is basically 6.02 into 10 to the power 23 atoms, which is Avogadro's number. 1 mole always contains Avogadro's number atoms or molecules. So 1 gram of uranium will contain the Avogadro number divided by the weight expressed in grams. It is 238 grams. So we get the atoms in 1 gram. Therefore, the decay rate, which is lambda times n, is this 0.693, which is natural log of 2, divided by the half-life, multiplied by the number n, and when we substitute all this, we get this answer. This answer is the number of reactions per second, number of decays per second, and number of decays per second is called Becquerel, and notation is BQ. So 10 to the power 4 decays are occurring per second, 1.2 into 10 to the power 4 decays for uranium, which is alpha decaying. 1 gram of that will have this much the reactions. Let us define the activity. For a sample containing radioactive material, the dN over dt is the average decay rate, and its units are the decays per second. People write it in dps form, or some people say that these are the decays per minute, and the dpm. Old texts used to write, and still are writing, that 1 curie. It's a value of a radioactivity if the sample is decaying at the rate of 3.7 into 10 to the power 10 decays per second. 3.7 into 10 to the power 10 decays per second are equal to 1 curie. The smaller units are 1 microcurie for 10 to the power minus 6 and 1 millicurie for 10 to the power minus 3. The standard international units for the activity are becquerels, and 1 becquerel decay rate is 1 disintegration per second. So 1 curie is equal to 3.7 into 10 to the power 10 becquerels, or in terms of the other way around, 1 becquerel is equal to 0.27 into 10 to the power minus 10 curies. These other units are the kilobecquerels, the mega becquerels, and so on. Remember that the decay factor we have derived and we have reached, the decay factor is e to the power minus lambda t. And this is a decay factor. It comes with the activity. It comes with the number of atoms disintegrating per second. So it comes with the radioactive decay. So it is called the decaying factor. It is the fraction of radioactive atoms that are after time t. People have tabulated, and in several books, the tabulated form of the decay factors are available. The decay factors depend upon the value of lambda or the half-life. So here we are tabulating the decay factors for technetium-99. You can see that it is a table in which the hours are written in this column, and on the row we find minutes. So hour 0 and the minutes 0 is this. Hour 0 and 15 minutes, 30 minutes, 45 minutes, then full hour, and so on are 1 hour and 15 minutes, 1 hour and 30 minutes, 1 hour and 45 minutes. Values are given. Intermediate values can be found with the help of interpolation, or you can use e to the power minus lambda t as a decaying factor formula. Let's move further and do examples. A container has a technetium, and it is labeled as 2 millicurie per milliliter at the time 8 a.m. Question asked is what volume should be withdrawn at 4 p.m. On the same day to prepare an injection which will give 1.5 millicurie for the patient. Now, using the table earlier, we have for the decaying factors of technetium 99, after 8 hours, you see, after 8 hours, the value is 0.397. So concentration of activity is 0.794 after 8 hours. From 8 o'clock to 4 o'clock, the total time is 8 hours. And for 8 hours, we have the answer that the concentration will reduce from 2 millicuries per milliliter to 0.794. Now, volume required we must find, because we want this much injection, 1.5 millicurie. So 1.5 millicurie divided by this will give us 1.89 milliliter will be the volume to prepare the injection that will be given to the patient, and it will produce the required millicurie dose. Another question is, now, what is the decay factor for the technetium after 16 hours in the above case? Now, you look at the table. I go back to the table. And here we have up till 11, but we have the 8, up till 8, up till 6. So we can convert that. We have total 16 hours. So 6 plus 10 is this. The factor for the decay factor for 6 hours and the decay factor for the 10 hours. And these two decay factors will be multiplied, because e to the power minus lambda t multiplied by e to the power minus lambda t2 will produce the result, and this is the answer. Here, remember that these two factors are multiplied, not added, not added. Other combinations of the time will provide the same result. Now the example says we have a vial containing technetium-99, which is labeled 3 millicurie at 3 p.m. What is the activity at 8 a.m. on the same day? The decay time is minus 7 hours. From the table, we find the decay factor for the 7 hours equal to 0.445. Therefore, the decay factor for minus 7 will be 1 over that, and it is 2.2. We multiply with this and get the 6 millicuries, 6.7 millicuries. Remember that if we have to go back in time, this is a 3 p.m. we measured, and the activity at 8 a.m. was prior to this activity, and then it will be larger than this value, the 3, and it comes out to be 6.741, because the factor for minus time will be 1 over that. Now we do one more example to find out the decaying factor after 8 hours for technetium using a pocket calculator ourselves. The half-life for the technetium is 6 hours, so natural log of 2 divided by the 6 hours will give us the time. Total decay time is 8 hours, then lambda into t is this much, and the answer for the decay factor is 0.397. Let me briefly talk about these graphs and the way we plot. The decay factors, when are plotted on such a graph paper. So look at the paper. Paper on x-axis has the number of half-lives. 1, 2, 3, 4, 5. All are changing with a fixed width and the fixed difference of 1, 1, and so on. And as we see these differences, they are linearly changing. On y-axis, the decay factors are plotted, and the scale is changing. This interval, as compared to the other interval, is large, and it subsequently is going to smaller values. Such a scale is called logarithmic scale. The values are in log, showing their behavior in log. The values are actual values. For example, 0.1 is this 0.1. A 0.2 is this 0.2, and so on. They are actually, you have not taken any log on them, but they are really on a logarithmic scale. So if you plot the factors, the decay factors are e to the power, or this number of atoms decaying in a radioactive material, then they show a straight line. This indicates that they are decaying exponentially, because logarithm scale on x-axis or y-axis actually does change the behavior. So this is a useful graph for the decaying curves. And the straight lines of such type are really plot on semi-logarithmic graph. One scale is logarithmic, the other is not. You have the different types of graph papers. One is this linear and linear. X-axis is linear, y-axis is linear. Such a graph paper will produce the actual whatsoever is. And if you plot the decaying behavior, it will be exponential decay. This is a linear graph paper on x-axis and logarithmic graph paper on y-axis. These are called, basically, these are the periods. The 1, 2, 3, 4, 5 periods or cycles. So this is 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5th. So 5 cycle logarithmic graph paper, a semi-logarithmic graph paper, because y-axis is log, but x-axis is linear. If you have this kind of a graph paper, it is on x-axis a logarithmic and on y-axis also logarithmic. Look at the cycles. On x-axis, there are 2 cycles, 1 cycle and another cycle. On y-axis, there are 1, 2, 3, and 4 cycles. So log scales can be varying and with the different cycles on a log-log graph paper. These graph papers are extremely useful when you have relationships that are obeying log on y-axis and x-axis also having a logarithmic behavior. Now let's talk very briefly about the specific activity. And radioisotope samples have a specific activity. Remember that isotopes that are radioactive have also some stable isotopes as well. So when a stable isotope of radionuclide are present in the sample, they are called carriers. And the sample is said to be with carriers. And if sample does not contain any stable isotope, then the radionuclides are called carrier-free. And radionuclides can be produced carrier-free or with carriers. It depends on the use. The radio activity of the radioisotopes of a total mass of elements present in the material is called specific activity of the sample. The specific activity has a units of curies per gram. They can be expressed in the other units of liters and per gram and multiplied by curies. The highest possible specific activity of the radionuclides is its carrier-free specific activity, written as C, F, S, and A. This is a carrier-free specific activity, and this can be calculated very easily using the basic properties of the radionuclide. Here we try to show this for a few things. Suppose there is a carrier-free sample that is available, and it is 1 gram of radionuclide X with the mass number A, having half-life T. The atomic weight of the radionuclide is approximately equal to A, which is its mass number, and the sample contains A grams of radionuclide, then it will be approximately equal to 6.02 into 10 to the power 23 atoms, the Avogadro's number. Therefore, 1 gram of the sample will contain N equal to the Avogadro number divided by A. So, the decay rate of the sample, dN over dt, will be dPs equal to activity multiplied by N, the lambda times N. And we can therefore find out the activity A in terms of the curies, and the expression, if it is simplified, can be written as a specific activity for the carrier-free samples. And this will be the activity per gram. The sample activity per gram for a material which is carrier-free is given by this 1.3 into 10 to the power 8 times A is the mass number multiplied by the half-life. Half-life is given in days in this expression, and one can change in the other units. The equation also gives the activity in millicuries per milligrams or microcuries per microgram. Let's do one example for this kind of a calculation and try our best to find out what is the specific activity of iodine 131 and technetium for carrier-free material. The specific activity, carrier-free specific activity in curies per gram is given by this. For iodine, A number is 131. Half-life is 8 days. We use the equation of 8 days and write it down and convert. The answer is this, 10 to the power 5. For technetium, A is 99. Half-life is 6 hours, which is 0.25 days. Substituting this, we get 5.3 into 10 to the power 6 curies per gram. Remember that these things are very useful in terms of curies per gram is basically the specific activity, and carrier-free specific activity will be the largest possible activity that sample will have. Then if we know how much grams are being used, then we can find out the absolute activity. Let us stop this discussion of calculations of the radioactivity here. We will move further to find out the age of things using radioactivity in coming lectures. Thank you so much.